Welcome everybody to the lounge room. We are starting the first speech of the day here, and our speaker now is Daniele Bagni, who is HPC customer engineer at AMD. He always have worked in digital signal processing for computer vision, and in particular in the last 20 years of experience, he devoted himself to FPGA. In his free time, he likes playing sax. And Daniele, the stage is yours.
Thank you very much. Good morning, everybody. So, first of all, thank you to Alessandro for all the good words that thought about me. This is probably the last time that I will talk about FPGAs, because after 20 years I decided to move to a completely different world, from digital signal processing on FPGAs to high-performance computing, which is completely different kind of things. It's like I was working on the extremely small, the embedded, what is called edge, and now we'll move to the extremely big, what is called high-performance computing, clusters of GPUs and so on and so forth. So this is the last work I've done on machine learning about FPGAs, and was done around October last year. And I'm talking about a couple of tutorials that are published on GitHub related to how you would deploy a convolutional neural network starting from the original model that you have in your PyTorch or TensorFlow or whatever, and then you run it real time on the target board, in this case provided by Xilinx. Xilinx is the FPGA vendor that AMD acquired, and if you want to laugh, I moved from Xilinx to AMD, I had to resign from Xilinx, and I have to sign a new contract in AMD, because they are completely different entity, and that's why it wasn't just a simple move, Daniele, from here to there, as I thought at the beginning. Anyway, let's go on. This one? Yeah. Okay. My God. It's difficult to see. Maybe I stay here, because in that case I can. Okay. So, number one, why somebody should be so crazy to do AI on FPGAs? This is a very important question. Everybody knows GPUs. GPUs are the natural machine to run AI, to run machine learning, okay? What is the AMD or Xilinx solution to do that? Our software tool is called Vitis AI, and we have a neural network processor unit that runs on our devices. And then to show that, I will give you a view of the flow using a couple of simple examples. One is a ResNet classification example, just to show the flow, and then something a little bit more complicated, which is object detection using YOLOv5. Then we will summarize everything with the key takeaways, and I will show you what is new into our development flow. Of course, you're free to interrupt me, providing that we have a certain amount of time that maybe is better I take in time with the timer here. And okay, thank you. Feel free to interrupt me when you need some more clarification. Okay, FPGAs. FPGAs are still needed. The world is big. There are many different applications. There are many different constraints, and GPUs are not the solution that fits everything. Okay. So there are applications or classes of applications where you need low latency and deterministic inference. You don't want to have an OS that doesn't enable you to provide the answer in a certain amount of hundreds of microseconds or fractions of milliseconds. In that case, this is the classical place where the FPGA runs a good fit. Then, of course, power consumption. GPUs are normally known to be extremely hungry in terms of heat. They consume a lot. On the other hand, FPGAs are very efficient from the ratio of teraops divided by watts. Flexibility. An FPGA is a programmable device. Every time that your network or your needs are changing, you can change what you map inside the FPGAs. And you can do this working with the very high-level abstraction languages. The story that you must be a Verilog or VHDL expert is gone. It's gone from decades. I always work in this company using only C++. And in C++, I program by FPGAs for the records. And now we are going to Python and to something even higher level. Okay? Then the FPGAs offers you integration. Integration is the magic words of why FPGAs are still good for these kind of things. For example, you have the classical FPGA side, which is what we call PL, programmable logic. But the FPGAs of today are totally evolved. They are different from the ones of 10 years, 20 years ago. They are now a monstrous system on chips that contains different ARM CPUs. Then they will have the programmable DSP Mac engines that can be programmed at a micro level. And you will have AI engines. AI engines are something that we patented. They are very long instruction word, 1024-bit, single instruction multiple data vectorial machines. Those are the machines in which you can basically put all the tensorial mathematical operations because of the single instruction multiple data architectures. And by the way, these machines are not only in our FPGAs, but they are also in computers that you may buy from our partners that contains AMD devices like Ryzen AI. Ryzen AI has an integrated GPU plus the NPU that is based on the engines, okay? For example, to run large language models and so on and so forth. Okay. So, for an hardware like this, you need a software development flow. The software development flow that we provide is called Vitis AI. And basically, this allows you to work on your typical frameworks for machine learning, which are TensorFlow, PyTorch, ONNX. And based on that, you will have tools to quantize the network. The network officially is developed in floating point 32-bit, typically. If you want to run it with a high throughput and low power consumption, we recommend to quantize it to 8 bits. But recent tools that we provided into the market now, we also accept B floating point 16, floating point 16, together with the int8. We offer two techniques. One is called post-training quantization, where you basically inject some calibration data and then you quantize the network. Another one is a fine-tuning one called quantization-aware training, where basically, in the few cases it may happen that in which you don't get the accuracy, the prediction accuracy you like to have in comparison with the floating point original model, you can do a fine-tuning with another training in order to increase and to recover from the losses that you had. The output of all of the, based on everything then runs on APIs that we call Vitis runtime APIs. Those APIs enable you to program either in Python transparently or in C++. Typically, our customers, especially in automotive applications, they want to have maximum performance, and once the prototype is good at Python level, they move then the implementation into C++, compiled code. And then everything is running on the neural processing unit, which is an IP we provide to you, but you have a portfolio of IPs that you can select depending on your cases, depending on how many engines you want to use and what is the trade-off between resources that you will apply in the FPGA versus the frames per second that you want to achieve on your neural network. Okay, and the output is what we call a snapshot. Snapshot is a kind of package that contains the quantized network, the weights, the instructions of the neural processing unit, plus a lot of metadata that enable the neural processing unit to run. Okay. The tutorials are based on Vitis AI 5.1 release that was released on October 25. Now we have Vitis AI 6.1 that was released in March of this year. And that's why I didn't update it. I was busy with other things. And probably in October, we will have Vitis AI 6.2. Okay. Good. What is the NPU? The NPU architecture, or neural processing unit, contains a small part of programmable logic FPGA to fade the data from the different interfaces, DDR, whatever they are, PCI, etc., to the engines. The engines are the places in which you have this monster of single instruction multiple data vectorial units that will run the mathematical operations on tensors. The engines, for the records, is programmable in C++. So there are crazy people that I know that were able to not using this kind of flow, but just program the network they wanted to do directly in C++ into the engines. In that case, even achieving higher performance than what we can achieve using this flow, which is more high level. This flow is really for scientists, for people that don't want to touch the hardware, like me. They want to stay in C++, Python, TensorFlow, PyTorch, high-level things, because you want your brain to be, let's say, focused on things you like and not getting boring at very, very low level, okay? However, I would consider C++ low level in any case. I'm old, that's why I like low-level things, okay? Int data is the format of the quantized network, at least for these two tutorials, but as I said, we offer now also bfloat16, okay, to achieve higher performances in terms of accuracy. And as I said, you will have a runtime APIs that enable you to talk with the hardware and to abstract the hardware below, because you can have different NPUs depending on the devices you want to use or depending on the resources that you want to apply. Okay, let's go on. This is a picture that I took of the board in itself. Every development environment has some target device boards or some development kits where you want to, sooner or later, to put your code and to run it. What happens? Typically, you will have an environment which is a Ubuntu OS or any type of Linux OS, and in that is your host device, host environment in which you develop everything. And later, you will put the application on the target board. The environment typically that we provide is based on Docker. So you can have Docker images for SUSE, for Red Hat, or for Ubuntu. The Docker contains all the flows that I showed you before, so all the dependencies are already resolved. You don't need to become crazy to solve those kind of issues. Then the environment offers you a cross-compilation, because you are working on Ubuntu computer, x86, but you're compiling code for a target board that contains ARM. This is cross-compilation, okay? You need to do this cross-compilation through our SDK, and once the L file is ready, you can basically upload it together with the images that you want to apply, together with the snapshot. You use SSH, SCP, and you send the data to the board, and then from that moment, you run the board using a classical UART terminal and so on, okay? Okay, let's see now the first example. The first example is image classification with ResNet18, just because we want to show the flow. The example is trivial. You guys work on LLM or stuff like that. This is prehistory now, okay? But 5 years ago was not prehistory at all. And it's not even prehistory now, because in the embedded, ResNet50 is still a big beast to be treated. And YOLO are also even bigger beasts, okay? Let's go on. So, this is ResNet18 that was basically retuned using my God, I forgot the kind of fine-tuning from. I took a network that was trained in ImageNet with 1,000 classes, retrained it using a smaller data set like this vCore, which contains more or less 7,000 images. And with transfer learning, that was the terminology that I missed in my brain. I basically retrained it using probably some epochs, and to decrease the amount of classes, and basically tune the network only to 15 classes. The purpose here is that you got a car, and you want to recognize the color of the car, as an example. So you see below the classes. The input image size is the classical one of ResNet, so 224 by 224, RGB, 8 bits per channel. And okay, then the framework is PyTorch. You open the Docker image from AMD, you train the network, you do the faster the transfer learning in PyTorch. And this is the amount of images. The training was lasting 36 epochs. And very important, the preprocessing. Preprocessing required the pixels to be normalized between 0 and 1 and to be RGB. Preprocessing in the training must be matched by pre-processing in the runtime execution. You believe it, you're younger and you probably are starting to laugh, but you can't believe how many issues I had with customers doing this mistake. Oh my, nothing works here. In the host, everything is fantastic. In the board, nothing works. What the hell you are selling to us? Sorry. And then you discovered they made a lot of mistakes in mismatching the pre-processing done in the board together in comparison with the pre-processing done during the training. Okay. Then you have to generate the snapshot. How you do that? The Vitis AI flow enables you to do this in a very transparent way. Basically, you use an environmental variable called Vitis Software Snapshot Directory, in which you point to the directory in which you want to create the snapshot. And then you put this variable ahead of the command line that you want to use. In this case, Python 3 test, my file which is doing test.py, which contains the inference, okay? And the flow captures naturally and transparently to you what is going during the inference process, and will create this snapshot. That's why I'm saying you're using your Python original code as it is without any single command change it. And believe me, this is not granted, because before arriving to this solution, since it's 10 years that we are developing these things on the FPGAs, we had solutions in which you had to change 50 or 60% of the code, which is something that you don't want to do, because you have spent so many efforts and difficulties in solving issues with the natural code, and then you have to do adding APIs you don't understand simply because somebody else tells you that if you want to run your software on my device, you have to change it. Oh my God, nobody likes these kind of things, okay? Great. Of course, since we provide many IPs, there are several variances of this neural processor unit, you have to specify the snapshot for that unit specific. In this case, this name means that I'm using the full array of AI engines that is composed of 304 AI engine shells, or tiles, as we say in our terminology. And so this is the biggest core. Of course, there are many cores much smaller that you can run even in parallel and so on and so forth. This is just an example. Once the snapshot is created, this is related only to your core, and you cannot use on a different core from that. You have to recreate it, okay? Great. From the host to the target is very simple. As written in my tutorial, you copy the vartml C++ code from the Vitis AI repository in GitHub to the tutorial. You cross-compile, and there is an SDK script plus a makefile to do that. Once you have cross-compiled the application, you copy the snapshot and the executable to the target. You copy the images for your test and the labels, okay? And then you can run the executable on the board using a command line. And again here, I'm emphasizing this flag, color format equal to 1, which is a flag in which I swap the BGR data. OpenCV, unfortunately, likes to read the images in BGR, which is different from RGB. And if you don't do this swap, then you will have mismatches again, and you say this inference doesn't work at all. But the NPU is working pretty well. Is the data which are changing, and also these kind of things make a good system to fail. Okay. That's why it's written in red. Okay. Now, this was simple. Classification stays, all the graph stays in the neural processing unit. However, for this case of object detection, things are a bit more complicated. And here is where the heterogeneity of the FPGA makes sense, because you will see that a part of the graph will run on the CPU, while the remaining part of the graph, the most sensorial one, runs still on the neural processing unit. Okay, let's see. This is a YOLOv5 small that again was taken from the classic YOLOv5 trained with Coco, which has 80 classes, and was again using transfer learning retrained to decrease the amount of classes to only 5 vehicles. that are there, car, bus, ambulance, motorcycles, and truck. The data set was taken from RoboFlow. It's called the vehicle open images. And the image sizes are 640 by 640. And we are using the so-called COCO-JSON format to measure the mean average precision, MAP, which is the figure typically applied here for object detection. Okay, very important. Object detection is a bit tricky because there are many formats. Specifically, COCO, which is a good, very good, COCO provides PyCOCO tools, which is a Python library to measure mean average precision for, so you understand how good is your network or not. COCO applies this format, so basically the bounding boxes are formatted as XY, width and date of the top left corner of the bounding box, not normalized. However, YOLOv5 outputs something different, outputs a center-based normalized values. So you must be sure that you do the right conversion between these two formats. Otherwise, every mathematical mismatch that you are putting there will reflect in a mismatch in the predictions. And this is very, very critical here. Again, I'm using the COCO standard to measure the MAP, which means from 0.5 to 0.95 of the IOU intersection of unions, okay? And it may happen that if you use PyCOCO tools, you will have some deviations from the values that you measure with the Ultralytics original code, because YOLOv5 comes from Ultralytics and was training the Ultralytics framework. That's, again, no changes to the code, as I always said, okay? Great. What happens when you use the Vitis AI compiler? The compiler analyzes the graph and realizes that there are a lot of things like the backbone and the detection heads of the YOLOv5 graph that can run on the NPU. But there are some small things that we call tail. Those are the way to decode the three output tensors and then to send the data to the NMS, non-maximum suppression, that must run on the CPU. So the output tensors are three. In this case, for the image size resolution, they contain 8x80, 4x40, and 20x20 feature maps. And we apply a new environmental variable called Vitis AI quantization NB images. This tells you how many images you can apply in the so-called calibration. Calibration is you send images to the flow. The flow analyzes the images, captures statistics, and then tries to apply a better quantization in order to fulfill the statistics of images. Which, of course, means that if your images are all, let's say, a stupid example, dark, and you inject extremely bright images, you will make the calibration to fail. Okay, that's why normalization, blah, 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 those kind of things, a lot of image processing is better, has to be applied to avoid this kind of biases that a naive user could do, okay? The fact that you have 5 classes only means that the final channels are only 30 instead of 255 as the COCO, because the COCO has 80 channels. Okay. Now, you train it using the Ultralytics framework in PyTorch, I don't remember, in Python. Then the data set is extremely small, only 627 images. And basically, the YOLOv5 format is the one shown there: class ID, center X, center Y, width and height, normalized. And the training, the transfer learning was done using 20 epochs and a batch size of 32. This is for the training, okay? In order to make the network to become from 80 classes to only 5 classes, to make it simple. And if you want to understand better, there is a fantastic PyImage search tutorial, public, that explains how to change your network and how to do a better training and those kind of things, okay? Great. Once you have done this, you can basically take the Python code and run it directly on the board. At the beginning, I left everything in Python because I wanted to be sure of the prediction accuracy. So in the tutorial, we will have a couple of .py files. One is the NPU runner, where you basically run the NPU processing unit to launch the inference, and then in the other one you do the post-processing. Then I merged everything together to make it more simple, and this is the third Python code that you can apply. Of course, before doing that, in the environment of the board, which is Ubuntu, is embedded Ubuntu, you must import with pip, the ONNX runtime, Torch Vision, and PyCoco tools packages in order to enable the Python code to run on the embedded environment. And finally, you launch the inference with Python 3, the same code that I mentioned, and then you point the snapshot, you point the JSON file of the annotation that you want to use, and so on and so forth. Okay, so what you have seen so far, we have seen from one side a classification example that where the entire network was fit on the neural processing unit. Okay, the entire graph was there. You have seen that this is a simple example where I basically have only class scores. The object detection was a bit more complicated because you have many more output, the bounding boxes, the classes, and so on and so forth. And you have seen that the split was NPU running most of the graph, but CPU running NMS and running also some decoding layers that were not fitting well in the graph. Why? As I said, the AI engine is a vectorial machine. You cannot put spaghetti code if then else, if then else, if then else. This doesn't, is not, the machine is not done for those kind of things. Spaghetti code has to be executed in some more RISC-like processor and not in a vectorial machine, okay? Great. Now, this is, if there is something that you may eventually remember of this talk, is this slide. Because this slide summarizes the entire flow in 5 points. The flow is, we offer you a Docker image that contains the full environment, okay? Normally, you have to apply our, let's say, a script like that, and we recommend that you match your working directory with a certain workspace so that from externally, you can put things in that workspace, and from internally, you see you can share basically the same file system from the external world and the Docker world, okay? Then you set the NPU that you want to use. Then you do your machine learning work, training, inference, development of the network, of the model, etc., etc. Then you generate the snapshot, and during the snapshot generation, the network is quantized, okay, for you, basically. Then you cross-compile eventually the C++ application if you want to work in C++, or you do nothing if you want to remain in Python, and you just port everything there from the host to the target, and you run, okay? Okay, takeaways. Pre-processing is very important and critical and must match what you have done in the training. Snapshot is model plus weights plus calibration plus metadata plus instructions that will be generated, transferred to you from the tools. Of course, fewer classes means higher quality and less quantization sensitivity. Quantization can be, let's say, solved using more images or eventually quantization-aware training when in the few critical cases that I've seen. And you have seen that the YOLOv5 was split into different parts, subgraphs, one in the NPU and another one into the CPU. So the part in the CPU could be eventually, you could think, I have an FPGA, the FPGA contains a lot of resources, why I couldn't put an accelerator to do that part of the tail that doesn't doesn't fit into the NPU. Okay, and this is exactly what, I skipped this because I've said many times, but this is what we have done now. In the new solution, in the new Vitis AI flow, we have improved the compiler, and now we can have YOLO networks like YOLOv8, YOLOv5, they stay completely in the graph, into the NPU. So no tails, no split, and nothing anymore. and by the way, with the same accuracy using bfloat16 of the original floating point model. So 0% of difference between the embedded and the original model. For the YOLOv5, the compiler was able now to put on the engines the tails in bfloat16. And in that case, again, we have a very small depreciation of accuracy, less than 2%, and a single graph. And as I said, the much more important thing is that now we allow mixed precision, so you can have layers of your network in int8, followed by layers in bfloat16, where it matters. And this enables you to basically stay with the high accuracy, high prediction accuracy, and applying, putting everything into the AI engine part of the graph of the NPU neural processing unit. Okay, and last but not least, we have now added an AMD AI analyzers that enable you to understand where are the bottlenecks of your graph. And we support also the AMD GPUs, because Docker, if you want to do training into the Docker images and you're using CPU, this will become slow. Now, since a lot of CPUs, a lot of a lot of x86 contains AMD GPUs, typically Radeon, okay, you can use our GPUs to accelerate the training process. And with that, I think I have finished. Oh yeah, here are a lot of links that you have in the presentation, and this is the link to the newest 6.1 release. October there will be 6.2, and that's all. Thank you for your attention.
Thank you, Daniele, very interesting. And we have 5 minutes for a couple of questions. Do you have something to ask Daniele for us? Okay.
Thank you, great talk. I'm a company, we were looking at Xilinx inference server for serving models, basically. Is this technology capable of also serving models, like the server GPU-based? Okay.
It's a good question. No, the FPGA, we leave FPGAs only for embedded application. Servers, we have MI200, MI300, those kind of data center things that in which now I work. FPGAs are not good for that. And we have to be honest.
Okay.
Hi, thank you for the nice talk. I have a question, it's more maybe a curiosity. As a company, AMD, are you planning to work also on a proprietary deployment format, like, I don't know, Executorch or TensorRT, like to optimize more the graph
Okay,
or the memory layout? And
okay.
if it's
not related to this talk, I would say, but more in my new role related to high-performance computing. Yes, of course, we have our version of PyTorch that leverages, for example, our IP. This is another story. Our low-level software that recognize our GPUs, okay? Our GPUs are very complicated, several GPUs altogether that compose what people think is a single GPU, but in reality they are more. And the software has to be aware of this. And we have a library called HIP that is also, by the way, public, and everybody can work on this. And this library enables you to abstract the hardware, and you could eventually put the solution either in NVIDIA GPUs or AMD GPUs, okay? And this is just one example, but we have many other things like that we are developing for our GPUs. And for the user, basically transparent. If the user doesn't want to know what is running under the hood, but if the user want to understand, you can leverage it and add even more optimization with some manual work. Okay, have I answered to your question? Okay.
Any other question? Ooh. Nobody? Don't be shy.
You talked about the deployment environment and customers. So what are some real use cases you use this stack to deploy to?
Absolutely. You have to think that I worked on lane departure working system algorithms using classic computer vision for 6 to 7 years. And then neural networks arrived. And then everything was replaced by neural networks. Okay, this is just the 2 stages of an image processing pipeline. And of course, automotive. Automotive contains where, I forgot to say something which is important. FPGAs have an extremely long lifetime. When you produce something, you want to be sure that for 15 years, you will have the device that you need and the same device from now to next 15 years. Plus safety. Safety is something that I consider extremely boring, but there is a lot of protocols that you must fulfill. If your device is to be safety compliant, don't ask me what does it mean because I don't know. I consider boring, but this is important and extremely complicated also, and most of those FPGAs have these safety features. And so, yes, automotive are one of the classic applications, but also others are medical or military a lot, okay? To give an example.
Any other question? Okay.
Hi, thank you for everything. I have a bit of a more technical question. I was wondering, because before you talked about int8 quantization, and I was wondering, does the NPU support both per channel and per tensor quantization? Or does it only support per channel? Sorry, per tensor.
This is a good question. That honestly I don't remember because it's 6 months I don't touch this stuff anymore. Okay. And frankly speaking, I don't remember what I've done 1 week ago. So I encourage you to have a look at the GitHub place where there is documentation. If you don't find what you send me an email and I will try to find an answer for you. Yeah, it's very technical and honestly I don't remember the details.
Any other question? Okay, so thank you, Daniele, for your amazing talk.